Hi, I'm Jonathan Oxer, and this is SuperHouse. Now, one of the most common questions I get is how I made my light switches. In the last episode, I showed you how I made a rack-mount light switch controller, which has got an Arduino in it, and it reads from a whole lot of switches around the house, and then publishes those events to MQTT. But I didn't really show you much about the switches. So this episode is all about how you can make your own home automation light switches. So in the last video, I very briefly showed you a history of some of the buttons that I've made in the past. Starting with this one. This was the very first home automation button that I made. You can see it's got lots of hand assembly, and it's connected to an Arduino with an Ethernet shield on it. And that way what I could do is run Ethernet up to the back of the light switch, plug it in, it'd be powered using power over Ethernet, and whenever one of these buttons is pressed, you could send a signal to an MQTT broker or whatever else you want to do on the network. But that was quite painful to put together. Lots of hand assembly. Hand assembling all of these is a real pain. So I quickly replaced that with these custom-made circuit boards. I just designed a board that took those illuminated buttons, brought everything out. So this is an updated version. Once again, power over Ethernet support. This is on an Ether 10. It's a board which is an Arduino, basically like an Arduino Uno with built-in Ethernet, and that was designed pretty much for these light switches. And there's just different versions, so I've got one with 4 buttons here. This one is 6 buttons, 2 buttons. In fact, the way I had this originally was that I had an on button and an off button. It wasn't just toggle. So on this panel, which has got 2 buttons on it, that was just for one light, so it'd be turn it on, turn it off. And this one was first light, on, off, etc. That was just a different scheme. Rather than having a single button that you press it and it turns the light on, press it again, turns the light off, which is what I've got to now. Originally when I did this, I thought this would actually be simpler. I mean, from a software point of view, it makes no difference. You can send an event on every button press or on alternate button presses or whatever, but I had the idea that it would be easier from a user interface point of view to have an on button and an off button. And then people can understand, and they get a definite response. They know that if they press this, doesn't matter how many times they press it, it'll always be sending the off command to the light. But it just ended up being really confusing. You can see here it's got 6 buttons on it, and that was for controlling 3 things. And people would just look at this and go, I don't know what to press. Makes no sense. So that was a bit of a bad design decision, but that's just the way I did it in the first round. Now when I decided that I wanted to remove all of the overhead of having the controller and everything located at each light switch, this was my first experiment with it. It's a couple of push buttons, so this is for controlling 2 lights, it's not an on button and an off button. And all I did was connect it up to an RJ45 connector so that I could plug it straight into the same network cable that I was using before, but it's not running Ethernet. It's just using the network cable as a really long extension to connect these buttons back to an Arduino, and that's centrally mounted. And that's what the last episode was about, with that Arduino light switch controller. So what I've got here is just power. So it's got a ground connection and a 12 volt connection. The 12 volts is only used for running the illumination on the buttons. It doesn't do anything else. These particular buttons have built-in current limiting resistors. So all you have to do is apply 12 volts across them and they glow. And then the other lead here is just to a digital input on the Arduino. So there's one digital input coming from this button, and there's one digital input coming from this button. And that's just from the normally open connection, which is bridged across to ground. So when the button is pressed, it pulls this digital pin down to ground. Let's have a look at the schematic of how that works. Now this may be just about the simplest schematic that you'll ever see. So what we've got is a microcontroller. This is, in my case, the Arduino Ether Mega, and that's what's in the rack mount controller. Now we also have out on the other end a push button switch. Very simple. Basically, you push it, it makes contact. That's all there is to it. So the microcontroller has a ground connection, and it also has digital inputs. So what we do is we just put a resistor in series, and that's just to provide a bit of protection. There's nothing really to that. connect that out to the button, then the ground connection also goes to the button. Very simple. We've got the button, the resistor, and that's it. Now internally within the microcontroller there is also a resistor, which is a 22K pull-up resistor, and that goes to VCC, so either 5 volts or 3.3 volts, whatever is appropriate for that particular microcontroller. That will tend to bias this input high if nothing else is being applied to it. So what you can see from this really simple circuit is if this switch is open, there's nothing applying any bias to this digital input, so it's going to be pulled high by the internal 22K resistor inside the microcontroller, and it will see the input as high. If you push this button, it just connects through the 1K resistor to ground. That forms a voltage divider, so it's low voltage, 1K resistor and 22K resistor. And basically this comes very close to 0 volts. So when the switch is open, it's high. When you push the switch, it's low. And that way the microcontroller can detect when the button's been pressed. That's really simple. That's basically all there is to it. Now because I'm using illuminated buttons, I also have an LED inside the switch. So the switch is a self-contained unit. It's got the contacts for the button and it's got pins for the LED. Now internally it has a current limiting resistor in the first version of the button that I used. So all I have to do is connect that to ground, and then in this particular case I was using 12 volts. I connect that to the other side of the LED. Now because this LED, I'm not showing a resistor here, but inside the switch there is a resistor which allows this to run on 12 volts. So if this button wasn't illuminated, we wouldn't even need this 12 volt connection. That's purely to illuminate the LED. And then this particular cable, in this distance, that might be 5 meters or 20 meters or whatever. That's just the cable that runs through the house. So in my particular case, this bit of cable is Cat5 cable, and it's carrying ground, 12 volts, and digital for the button. Now this part here is what's being done by the RJ45 breakout. So this basically is an RJ45 connector on this end. There's an RJ45 connector on this end. That's just the Ethernet cable in the middle being used purely as a bit of wire. So we have the assembly here, which is the button, and we have the assembly here, which is the controller. All you do is replicate that a few times and you've got it. Now on my switch panels that have multiple buttons, all I do is take extra lines through here, and then at this end I have extra buttons, and it's all starting to look really messy. But if you go back to what I originally had, just with the single ground and data and then power to the LED, that's really all there is to it. Okay, so now that we know that I'm crap at drawing schematics by hand, let's have a look at one on the computer. We'll do this properly. So this is the schematic for the 2-button version of the light switch. And in this particular case it's using an updated version of the button, so I've put a 3K3 resistor in series with the LED. But I'm getting ahead of myself. Let's do a recap of what we were just looking at. We have the ground connection. This comes from the microcontroller, so that's common ground for the microcontroller. And we can see that the buttons connect to that, and the LEDs connect to that as well. And we also have plus 12 volts coming from the controller, not the MCU itself, but supplied down the same cable that supplies the LEDs just to illuminate them. And then we have some data connections. Pin 1 here on the Cat5 cable goes to one side of this button, so when the button is pressed it just shorts pin 1 to ground. And remember, at the other end of this cable, that data line is being pulled high by the microcontroller using its internal pull-up resistor. So when this button is pressed it goes low, when it's open it goes high. And the same thing on data pin 2 for this button. Now if we look at the 3-button version, it's just the same thing. We can see here it's just got an extra button down the bottom, and now we have the data connection coming through on pin 3 as well. And the 4-button version, once again, it's just the same. It starts to look like a bit of a spaghetti mess just because there are so many connections here. So once again, we just got data connections going to the switches, and we have power and ground. So as you can see, the switches themselves are electrically incredibly simple. It's really just a breakout for the button with an RJ45 connector. But you ask, why did I have 2 ground connections and 2 power connections? If you look at the pinout here, look at this. I've got pins 7 and 8 connected to ground, and I've got pins 4 and 5 connected to 12 volts. You might say, hey, that's wasting a couple of data lines. You could have just used 1 ground connection, 1 power connection, then you've got 6 data lines. The reason for that is that I just arbitrarily picked the same pins as I used for typical DIY power over Ethernet. I had no particular reason for picking these pins other than making it the same. That way, if I accidentally plug one of these into one of my power over Ethernet injectors, it's just going to illuminate the button, no damage will be done. There's no particular reason for picking those pins other than the fact that they match the typical PLE pinout. Just for reference, this is what it looks like on the RJ45 connector. You can see we've got data 1, data 2, data 3, pins 4 and 5 are 12 volts, pin 6 is data 4, and then 7 and 8 are ground. So that certainly made things a whole lot easier, but it's still a bit of hand assembly. I liked this general architecture, but I wanted to be able to make these much more simply without all of these hand-soldered connections, flying leads, and sockets like this. So what I wanted to do was make something that would be really easy to assemble. And I did it by using these same buttons and then just making up a couple of PCBs that fit over the back and incorporate an RJ45 connector so that instead of having this hand-wired solution, I could just make one like this. So it's essentially the same thing. It's just that it has these momentary buttons mounted through the faceplate. They then go into this PCB, and also the socket goes into the PCB. By putting those together, that is functionally the same as this. Obviously it's a 3-button version, but it's still just the same thing. And I did versions of that circuit board so that I have 2-way, 3-way, and 4-way. And that way I could make up these little assemblies very simply and easily. Just solder in the socket, mount the buttons through the faceplate, solder the PCB on, and you're done. It's a really neat, very simple little assembly. It's really strong. All you have to do is plug it into the RJ45 connector on the end of the Ethernet cable, which then goes back to the central controller, and mount this in the wall. Really nice. But just as an aside, I also experimented with another version that used those same buttons, but did keep all of the logic in the central location, and included Wi-Fi. So, this, for example, is another circuit board that uses those buttons mounted through it, same mechanical assembly, but it's got a footprint here for a particle photon. I actually originally designed for a spark core, but then that was replaced by the particle photon. It's got a 433 MHz receiver on here, little piezo so I can give audible feedback for programming or whatever. And there's a daughter board that fits on the top of it, and that includes 4 output channels, and it's got a switch mode power supply here. So all you do is take off your normal mains cabling, plug it in here, and this just goes in place of a regular light switch, except that now it's got a microcontroller in it with Wi-Fi. This is the same version, it's just fully assembled. Well, it's actually an updated version of the PCB. You can see the red carrier board here. That's a second revision that I did. And it's got the particle photon in there. In fact, this is a particle photon, just in case you haven't seen one. It's a little microcontroller board that's Arduino compatible, and it's got built-in Wi-Fi. And in fact, while I was working on this, I wanted to replace these with an ESP8266. So I designed this little thing called the Core SP12. It's basically an ESP8266 on a little carrier board with a voltage regulator with the same footprint as a particle photon. And the idea was to make this a drop-in replacement. So anywhere that you'd use a particle photon, you would use a Core SP12. And that, for example, would be able to go into the back of the light switches, and then Wi-Fi on the light switches. So for anyone that says, hey, you should put Wi-Fi in your light switches, use an ESP8266, it'll be a whole lot better. I actually did that back in 2015. But I still ended up going with this other method that I'm going to show you now. So as I was preparing to do this video, I was going to order some more of these buttons so that I could, show you how to build them and maybe even make them available for sale. And I discovered that it was actually very hard to get these buttons now. I couldn't find a good supplier of them. So I've ended up basically updating the version of this circuit board to suit a different button. It's got a different footprint, it's still momentary, it's still illuminated with an LED. It still looks very similar, it's just got a slightly thicker illuminated section there. And also it doesn't have a current limiter in with the LED, so I have to do that externally. But basically what I've done is designed updated versions of these boards, and instead they have the footprint for this new type of button, this one. So let's see how we put those together. First thing you'll need is a blank wall plate. This is just like a light switch, except there's no switch on it. It's just designed to cover up a hole where you would have had a switch previously. You can buy these for a few dollars down at the local hardware store. Here in Australia we have a rectangular sort of style plate, which I think is pretty much the same as the US. In a lot of European countries I think the standard is more to have a square sort of faceplate. Just find something that's suitable for wherever you are. So I'm going to use these particular faceplates because they match the very common style that's used here in Australia. Now you also need to look at how much space you have, because you don't have the whole area of the faceplate. The actual hole that it mounts into will be smaller. This is a plaster mount bracket. So what's normally done is that a hole is cut in the plaster, this is slipped in behind it, so the plastic comes in front of it just here, and then the wall plate screws on the front. The result is that the actual space that you have, the hole that you're going to be able to put things in, is about 50 millimeters by about 75-77 millimeters for an Australian switch. So whatever you do, you just need to make sure that it fits within that space. So if you're mounting things on the panel, make sure they're going to clear the mounting bracket behind it. So to get the positioning correct, you can grab something like some painter's tape and put that across the front. So you could just stick this on here, use a ruler, draw a line down the center to get an accurate position, measure out the positions, that sort of thing. That's what I did for the first set that I made. But then I decided to get smart, and on the first version what I did was include dimensions on the silk screen. So here it's got 30 millimeters that way, 24 millimeters that way, center to center on the buttons. But that's really just a reminder to myself so that I could measure it out by hand. And when I had the PCB, all the documentation was right there. But then with this latest version of the buttons, I went one step further. I actually put a hole right in the dead center of each button location, so I could use the PCB itself as a template. So all I got to do is grab something like a little felt tip pen, put the PCB exactly centered on the board, and I can put the pen through the holes and mark it, and then I can drill through those holes. Now unfortunately, once the socket is mounted on here, it slightly undoes that benefit because it holds this up away from here. But by clipping these leads off, we can make it sit down. So I'll make this one a three-way button. It's got the leads slightly clipped off here. So what I'll do is get the PCB aligned dead center on the board, on the light panel, and then I'll stick my head in the way here, put the pen down through the hole. And now I've marked the center of each of the buttons, so it's just a matter of then drilling through these with a pilot hole to set the position. Now I've just used a ruler to measure up that last one. I'm going to do a single button version, so what I'm going to do now is make up 1, 2, 3 and 4-way button panels, just to show you each of them. But I don't have a PCB for the single button panel, which means I don't have a template. So I'm going to use the 2-button circuit board and make up a single button panel. Let's drill the holes first though. Now the accuracy of these holes and the clean cut is really important, because even like a slight misalignment of these buttons is going to be pretty obvious when you stick it up on the wall. That's why I used a drill press to do pilot holes first, then I can get the position really accurate. Then I have this 16mm spade bit, This is a brand new bit. It's really clean, very sharp. Now, if you use an old bit, it can tend to walk a little bit or tear at the plastic, so I keep this bit specifically for doing wall plates, so I get a nice clean cut through the plastic. Even with a really good sharp drill bit, you still end up with a little bit of burring around the edges. So then I just use a scalpel to clean that up. Got to keep the workspace clean. So now we have 4 neatly drilled faceplates ready for our buttons to go in. We just need to put those in. Now I haven't done these up tight. I've just very loosely put the nuts on place to hold the buttons in position, but the thing is that we need to be able to rotate them to get the orientation correct. If you look at the back of the button, you'll see there's a little dot on here which indicates the orientation, and you can also see that the pin spacing is different. The distance across here is about 9 millimeters. Across here it is about 8 and a bit. So they're slightly closer together that way, and the footprint on here it's actually more obvious because you can see the white silkscreen marking for the perimeter. These ones protrude out through it, these ones are almost contained within it. So what we need to be able to do is rotate the button to get it to line up with the footprint on the circuit board. The PCB itself also has markings on here for the orientation. And so what we need to do in the case of, well, let's pick this one. This is the 3-way button. I'm going to align it so that pin 1, which is where the mark is up sort of towards the top left. So in fact this one is almost correct. It needs to go about that way. This one will rotate around this way. This one rotate around this way. And get it so that the pins are aligned in basically the same pattern as the footprint on the circuit board. And then once you've got it pretty much spot on, just do it up a little bit more tightly. Still not really tight, just finger tight, but enough to hold it quite firmly in place. Now it's quite a tight fit. I actually didn't get the spacing on these pins quite right. I did offset it, but not quite enough. So getting multiple buttons aligned all at the same time, all with the correct rotation, and fitting through these fairly tight holes, is a bit of a juggle. But with a little bit of twisting and some slight adjustment on the rotation of the buttons, you can get it in. See, I've put it into this end button now, and you can see that the circuit board is actually slightly twisted relative to the main base, which means this button isn't quite aligned. So if I rotate the circuit board, that's now rotated the button and it's got its pins aligned correctly. So I can use that as a reference guide and try to get the others to match that alignment as closely as I can. A little bit of wriggling and it goes on. Now one other trick here is don't push it hard down onto the back of the buttons. Just push the circuit board on. I'm trying to actually pull it up a little bit now. Just push it on far enough that the tabs come through. I'll see if I can get it aligned so you can see straight down. I don't have the PCB jammed hard up against the back of the button. It's sitting out from it and it's over all of these little tabs or pins, and they just come through the PCB, but they don't go all the way through. And there are a couple of reasons for that. One is that it means that there is less strain on the base of those tabs. So if there's a little bit of misalignment, they're less likely to be bent or broken off. And the other is that if you look at the position here of where the socket is, these tabs come through directly below it. Now if I grab an Ethernet cable and plug it in here, you can see that it needs to clear the bottom. So we could either cut those tabs off, or we can just not put the board all the way in. The other thing to keep in mind is that when the network cable, which I keep saying network cable, but it's not actually network cable, I'm just using Cat5 and RJ45 connectors. So once it's in place, imagine that you are looking through a cross section of the wall here, and the mounting bracket is going to be in here through the wall. There's going to be probably 10mm plasterboard through here. So this cable has to bend up to clear and end up on the inside of the wall. And that means that we don't want it pushed down here because these buttons are actually fairly short. I'll grab another one out. They're not as deep as a lot of illuminated push buttons. They're fairly short, which means that it ends up very flush to the back of the panel. And we need to make sure that we have enough clearance that when you attach this to the wall, the plasterboard can fit through in here and the cable will go through without being, wrenched off or have too much pressure applied to it. So now I just need to do the same thing for the 1, 2 and 4-way buttons. I'll put the circuit boards on and then we'll solder them in place. And now we've got to the single button panel, which I don't have a specific circuit board for. But what I'm going to do is use the 2-button panel, and I'm going to put it into the button 2 position, not the button 1 position. The reason for that is if I use the button 1 position, it brings the network connector, or the RJ45 connector, really low down. The cable would come out down here. So if I put it onto the button 2 position, it locates the circuit board fairly high up like this, and then when the cable goes in, it'll be pretty much in the center of the whole panel, and there'll be plenty of clearance. So I'm using the 2-button board to make the single button switch. Now for most of these, for all of the multi-button panels, you'll find that just having the nuts finger tight is quite sufficient. They're not really going to go anywhere because they're all soldered to the PCB anyway. They're not going to work loose or be able to rotate. The exception is this single button panel. That's because it doesn't have anything to stop it from rotating. It can tend to unscrew a little bit. So you really need to make sure that the nut is done up really tight. And in fact, what I often do is get some hot glue. I just use a hot glue gun and squirt some glue over the nut. Make sure that goes onto the thread and onto the back of this wall plate as well. That'll stop it from unscrewing. Yeah, flow some solder into each pin. We're ready to test. So to test these buttons, what I'm going to do is plug it into the button controller that's in my garage. If you look at the controller that's just in here, you'll see that's very similar to the one that I showed in that last episode where I explained how I made it. The one that I showed in that episode is at the other end of the house, and this one you can see doesn't have the laser cut panel. I just used the original plastic cover that came with it, and I just cut the holes out. The one I showed in the video is much fancier than this one. But what I can do is just plug a cable into one of the spare inputs, and it's not going to do anything because that particular I've just plugged it in and powered it up. You can see the LEDs are illuminated, so that's a good sign. So the it's going to publish to MQTT when I press these buttons, and we'll see on the OLED that it's done that, but it's not actually going to change anything around the house because there's nothing bound to these button events. So there you can see that I'm pressing the buttons and we're getting events coming up on the OLED. So it looks good. These are all working. Now after changing over the light switches in my house to these button type switches, there's one really weird thing I've noticed, and that is that a lot of people just can't figure this out. Now if you have a switch on the wall that's just like a regular flick it up, flick it down to turn the lights on and off, that's no problem. Now this button is an exact equivalent to flicking the switch. All you have to do is press it instead of flick it. But for some reason, people find that really confusing. I don't really know why, it's just that's the way it is. Maybe it's just because we're so accustomed to an interface that works in a certain way. When you change it like this, it really freaks them out. Now the other thing is that because it becomes so easy to have buttons do different things, like you can have buttons to control a light in another room or in an adjacent hallway, you end up with multi-way switches much more commonly than you do with regular switches. So in places in your house where you might commonly have just a single light switch, you end up with a multi-way switch. And that also adds to the confusion. So it's really important to make sure that you make it as easy as possible for people to figure out what does what. When they're presented with a panel that has multiple buttons on it and no labels, it can be really confusing. So I often have visitors come to the house and say, I couldn't figure out how to turn on the lights, when all I have to do is go to the first button and press it, and that does the job. So to help make that a little bit more intuitive, particularly where I have lots of buttons on a panel, I've gone for a convention where the first button on every single switch is the lights for that room. So if you don't know anything else, you can just walk up, you know the first button you press is going to be the lights. And throughout the house we have motorized curtains or blinds, so the second button is always the blinds for the room. So lights and blinds. And then because I have lots of 3-way and 4-way panels, the extra buttons that control other things, I try to orient so that they are spatially in the direction of whatever it is that they are controlling. So if I've got an extra switch on here which is controlling something in a certain direction, I have it on that side. So for a 4-way panel, the bottom left button will be something that's in that direction. Just makes it a little bit easier to remember. So looking around the house, it's a bit like this. Lights, blinds, lights, blinds, passage light, lights, blinds, exterior lights, lights, blinds, passage light in this direction, light in the adjacent room, lights, blinds, step lights, and veranda lights. So for the sake of your family and guests that come to your house, it's a good idea to follow that sort of convention. Just try to make things as easy as possible. Now, if you want to be sneaky about it, you can set up your home automation system using regular light switches so that people don't realize that this isn't doing what it normally does. As far as they're concerned, it's a switch on the wall, they flick it, things will happen, they'll be happy. But you can still have home automation. Check this out. This switch has a common connection and the switched output. So it just shorts across those. It's not momentary like a button, but what I've got here is a couple of little bits of cable. So I'll just screw these into the connections that are normally across the switch. And then I have my board here, which is the PCB or the breakout for the 2-button switch. Now, just like the way I made the single button switch by using button position 2, I'm going to do the same thing but with this switch. So looking on the PCB, there are 2 pairs of connections. The pairs that are closer together are for the LED, and the ones that are further apart are for the switch. So all we have to do is put this PCB down over the top of those 2 bits of wire that I just pushed in. A little bit of a jiggle and we should be able to get it in the right place. And then solder it on. You can see there that it's in place. It's a little bit floppy. In fact, what I could do is make it a bit more sturdy by just reflowing that solder and sliding it down so that it sits more flush against the back of the switch. That'll give it a bit more mechanical support. I could hot glue it if I wanted to. It's a little bit more sturdy now. So I'll cut off the excess just to leave plenty of room. And the cable can now plug into here. And when you flick this switch, it's going to short across the connections just the same as if you press the button on one of these assemblies. Now, of course, what's going through your mind right now is that's a momentary button. You press it and release it. This is a switch. You flick it and it just stays shorted out. That's not a problem. We can fix that in software. This is the example sketch from the last episode with the button controller. You can see here that we have an array which stores the last button state for each of the 48 inputs. It just keeps a value of whether it's been pressed or not pressed the last time we saw it. And then if we go way, way, way down in the sketch, where was it? Down here somewhere, process button digital. What it's doing is reading from the input and then checking if the value of the reading is 0. That means it's been pulled to ground. That's what happens when the push button is pushed in. It only proceeds if that's the case. So in any other situation, it doesn't care what's going on. Then what it does is compare, and it says, was the last state of the button not pressed? But it is now, in which case we know we've detected a transition. So this is a transition from a not pressed state to a pressed state. And then it proceeds and does all of the other stuff, does the display stuff, does the publish to MQTT, and down the bottom it updates that array with the last button state. So in this case our logic is we're only detecting when the button transitions from unpressed to pressed, and then when you let go of it nothing happens. But it doesn't have to be that way. We could be detecting any transition. So here we're checking for the value as being pulled low, but it doesn't have to be. That could just be if it is not equal to whatever the last button state was. And if it's not, then we know we've detected a transition. Now there are a few other changes we'd need to make down in the sketch, but what this will do is allow us to detect when the switch changes from an off state to an on state and from an on state to an off state. And that way you get an event sent every time the switch is flicked, whether you're changing it from off to on or on to off. And a tiny little logic change like that lets us use switches in place of push buttons. Dead easy. Right now, as I'm filming this episode, I'm only hours away from jumping on a plane to go to China. In fact, I'm going to be really pushing it to edit this video and start it uploading before I have to leave. So unfortunately, I don't have time to make available some of these circuit boards. I'm going to do it as soon as I get back. But what I have right here are bags full of the 2-way, 3-way and 4-way breakouts, the PCBs that I use to make my light switches. So I need to load them up with the resistors. I need the surface mount resistors fitted on all of these, and then I'm going to stick them up in the SuperHouse online store. Unfortunately, I also don't have time to do the Patreon prize draw, so I'm going to do that after I get back from China. So for all of my Patreon supporters, I'm going to randomly pick one, and I'm going to send them a little prize pack, which will be some of my light switches, breakouts and things like that. Some stuff that's useful to replicate what I've done in this episode. So if you make your own light switches, I'd be really interested to see what sort of style you do. I'd love to see what my viewers come up with as well. I really want to see more of other people's projects, not just my own. So please post videos, photos, whatever you want to do. And until I see you again, go build something cool.